In the last few lectures, we have taken a look at the Lie groups, which are continuous groups which are parametrized by a bunch of parameters, and the group elements depend continuously on their parameters, not only continuously, differentiably, as we have seen before. We had also seen that much of the properties of the Lie groups, though definitely not all of them, could be encoded by the behavior of the group elements very close to the identity, and this led us to the concept of the Lie algebra, a vector space associated with a Lie group with a certain useful operation. Now, it so happens that many of the applications of this theory to physics actually involves Lie algebras more directly than Lie groups. So, for the time being, we are going to take a break from Lie groups and take a look at Lie algebras in more detail. We will not really be mentioning much about Lie groups in this and a couple of subsequent lectures, except perhaps in passing. We are going to focus more on the algebraic structure called the Lie algebra, which, as I've just said, is going to be very important in physics applications. While we are going to keep our discussions confined primarily to the concrete applications to physical systems, it is important to be able to at least have a passing acquaintance with the corresponding abstract algebraic concepts involved. So here is a hurricane 2 of the abstract algebraic concepts that we will need to talk about Lie algebras. The first one of these is our familiar topic, the group. Just a quick reminder, a group is a pair, a set G with an operation star, where star is a binary map, a map from G cross G to G, which is associative and has an identity and an inverse. We have talked a lot about groups before, so we are not going to labor this point any further. But beyond groups, there are other algebraic structures which are going to be very important. One such algebraic structure which may be a bit unfamiliar, especially to physics students, is that of rings. Well, just like group is a set with one operation, a ring is a set R with two operations, plus and star. And with the condition that R comma plus is an abelian group with the identity 0, which we call 0, and this essentially is nothing but something very similar to ordinary addition. And the important point is the other operation star works well with this operation plus, in the sense that plus and star are distributive, just like multiplication and addition are. So for all A, B and C belonging to the set R, A star B plus C is going to be equal to A star B plus A star C. Of course, here the plus and the star may be entirely different operations from our ordinary addition or multiplication, but they share with ordinary addition and multiplication this particular property. In addition to this, you must also have A plus B star C is A star C plus B star C. Note that we have not demanded that our multiplication operation star be commutative. So the second relation does not necessarily follow from the first one. It has to be stated as an additional property that we demand. Now, a ring may or may not have an identity as far as the product star is concerned. Remember, R, the ring, is always an abelian group with respect to the plus operation or the addition operation. And there, of course, you have to have an identity, which we are calling 0. However, a ring may or may not have an identity as far as star is concerned. If it does have an identity as far as the product is concerned, a multiplicative identity, then you call such a ring unital. So a unital ring is simply one in which both addition and multiplication has identities. And not all elements in this ring, in a unital ring, may have inverses. Note, of course, that if a ring is not unital and there is no multiplicative identity, there is no question of having a multiplicative inverse. All elements of the ring, of course, have additive inverses, which are called negatives of their elements, but all elements may or may not have multiplicative inverses. This concept, of course, can only make sense if you're talking of a unital ring. And in a unital ring, elements which have multiplicative inverses are often called units. Now, this is something which can be a bit confusing, because this should not be confused with the one, or something which we call the one, that is a multiplicative identity. So this terminology units is quite distinct, and if we were really talking a lot about rings, you would have to be very careful about this distinction between units, which are simply elements which are multiplicative inverses, and that one special unit, which is the identity element itself. However, rings are really not that much of an interest to us. What we are going to be more interested in is the next level of algebraic structure, and these are fields. A field in abstract algebra is actually a unital ring, a ring which has a multiplicative identity, in which star is actually commutative. That's one important condition. And all the non-zero elements have inverses. When I say non-zero, I of course mean elements which are distinct from the additive identity. Now, it should be pretty easy for you to check that the basic properties that we have talked about, the distributivity, the fact that R plus, and in this case F plus, the abelian group and so on, will immediately lead to this result that the additive identity 0 star any element of the field has to be 0. This is a result which can be easily proven from the basic axioms, which is why the additive identity can never have a multiplicative inverse. No matter what you multiply it with, you can never get the multiplicative identity 1. Now, this is something which should be pretty familiar to all of you from our experience with ordinary numbers. The only ordinary number which cannot have an inverse or a multiplicative inverse is the number 0. This is very similar, and the real reason behind that, the underlying proof, is exactly the same, because the properties that we are assuming, properties between star and plus, are really the same properties that we have for ordinary real numbers. In a sense, fields are generalizations of ordinary real numbers. Note that what we have said is 0 cannot have a multiplicative inverse, but if all elements other than 0 have a multiplicative inverse, that means that what we have is a proper ability to divide by every non-zero element, and this is what characterizes the field. Or put in other words, in a group you can only multiply, in a ring you can add and multiply but not necessarily divide, and in a field you can do all of this. So a field is basically a very abstract version of experience that we have with real numbers. In fact, the most common field that we are going to talk about is the set of all real numbers under ordinary addition and multiplication, and another one, the set of all complex numbers under ordinary multiplication and addition of complex numbers. Next up in our list of increasingly complex algebraic structures is something which is very familiar to all of you. This is the vector space V. And as you all know, a vector space is never defined on its own. It always comes with an associated field F, which in most physics applications is either the set of real numbers or the set of complex numbers. And this vector space V over a field F has two operations: plus, under which V is an abelian group, and dot, scalar multiplication, which takes an element of F and an element of V and returns an element of V in such a manner that these two operations have distributivity and other compatibility conditions. I'm not going to talk any more about vector spaces here, because I'm going to assume that all the linear algebra you have done so far, as well as whatever exposure we have had to vector spaces earlier in this course, has definitely equipped you enough to deal with whatever vector space notions we need. Of course, there may be specialized things in vector spaces that you may not have encountered before. We will talk about them when we come to those particular issues. Now, What we are actually interested in is a special kind of vector space which is called an algebra. An algebra is a vector space A, where A of course stands for both the algebra as well as its underlying set, where in addition to the standard maps, addition of vectors and multiplication by scalars, plus and dot, there is another map which I have denoted by a diamond here. There is a binary map from A cross A to A, which in a sense is a product. So an algebra essentially is a vector space where you can also multiply vectors. And this product operation is bilinear, is linear in both its inputs, and in addition to that, it plays well with vector addition and scalar multiplication, in the sense that for all x, y, z belonging to the algebra, x diamond y plus z is x diamond y plus y diamond z. Now diamond is a very nasty way of putting things, so I'm just going to say into. So x plus y into z is equal to x into z plus y into z. And also for all xy belonging to the algebra and all xi and eta belonging to the field f, xi x times eta y is xi eta multiplied by x times y. Of course, here you have to realize that there are many different multiplications at work here. In the product xi x, the product really is a scalar product of the vector x with the field element xi. In eta y, a similar scalar product is being done. There is a product of these two vectors according to our new product, the product of vectors in our algebra. Then on the right hand side we have xi eta, which is a product in the field, and you are multiplying this scalar, which you get by multiplying xi and eta, by the vector which you get by multiplying x by y using our new product in the algebra. As you may have realized, we have kept this notion of this product of two vectors rather open-ended, and we have not really put in too many restrictions on that at this stage. All we have demanded is that this product works well with the two operations that are already there in the underlying vector space which comes with every algebra. So depending on what other restrictions you put on this product, you have various different possible classifications of an algebra. A very important classification is that of an associative algebra. In this, the operation diamond or into of multiplication of two vectors is associative. So x times y times z is the same as x times y times z. On the other hand, if the algebra is such that this multiplication operation between vectors has an identity, some special vector in your set, multiplication by which always gives you the other element back, then you say that the algebra is unital. So we could have associative algebras, we could have unital algebras, we could of course have algebras which are both. In fact, two of our most important algebras, GL and F, set of all invertible n by n matrices with elements in the field F, as far as we are concerned, either real elements or complex elements, is an associative unital algebra where the product is simply the simple multiplication of matrices. Of course, GLNF is a vector space because when you add two n by n matrices, you get another n by n matrix, which gives you the vector addition in the vector space. You can multiply GLNF elements by scalars, that is elements from F, to produce new n by n matrices. But in addition, you can also multiply them. And this multiplication, like all matrix multiplication, is associative. It also is unital because there is an identity element here. And the identity element, of course, is nothing but the n by n identity matrix. In fact, SLNF, the set of all n by n matrices with elements in F and unit determinant, is also an associative unital algebra. These actually happen to be two of the most important algebras that we are going to discuss, simply because most of our elements of Lie groups as well as Lie algebras really were matrix groups and matrix algebras. So GLNF and SLNF are in a way all encompassing as far as these algebras are concerned, and much of our properties will basically hinge upon properties of these two specific algebras. But let us now turn to the kind of algebra that we really want to talk about in this lecture. The Lie algebra, which is a special kind of algebra where the product is different from the product that we have talked about so far. A Lie algebra G is an algebra where the product is called a Lie bracket and has a rather special symbol. It's denoted by a square bracket with a comma in between, essentially two slots where your two elements go, and this obeys the following. For every x in the Lie algebra G, the bracket of x with itself, x comma x, has to be 0. That's the first property. And the second property is, for any three elements x, y, z belonging to the Lie algebra, the following identity must work. The bracket of x with the bracket of y and z, added to the bracket of y with the bracket of z and x, added to the bracket of z with the bracket of x and y, must give you 0. Now these are very familiar properties of what we call the commutator, and you are all familiar with this. The first one is simply the statement that a commutator of an operator, for example, with itself is always 0, and the second one is nothing but this well-known Jacobi identity for commutator brackets. But let me point out at this stage that here we are talking of this bracket operation as an entirely abstract operation. In principle, we could talk about this without talking about any other operation, which so that this bracket comes out as xy minus yx. We are not doing anything of that kind right now. At an abstract level, a Lie algebra is defined just to be a vector space which has an additional product, and this product has these two properties. The second property, of course, is called the Jacobi identity, and the first property is simply nothing but antisymmetry of this bracket. If the bracket is antisymmetric, that is xy is minus y comma x, then it automatically follows that x comma x has to be 0. It so turns out that demanding x comma x equal to 0 also implies that x comma y has to be minus y comma x. And let us see a proof of that now. To see this, all you have to do is start from the bracket of x plus y with itself. Now this of course has to be 0 according to our defining property, but using the fact that this bracket, like all operations in an algebra, is bilinear, you can immediately break this up into 4 pieces. This breaks up into x comma x, y comma y, x comma y, and y comma x. And according to our defining property, x comma x is 0, so is y comma y. Of course, so is the left hand side. And this immediately tells us that x comma y and y comma x, these two brackets, have to be negatives of each other. So not only does this antisymmetry immediately imply that x comma x is 0, if you insist that x comma x is 0 for all x belonging to G, then the antisymmetry will automatically follow, which is why the first property is actually called the antisymmetry property for the Lie bracket. Now, as I have been saying, there is a very deep similarity between the Lie bracket's properties and the properties of the commutator. And that is actually not an accident, as many of you may have guessed. In many situations, the Lie bracket operation really is a commutator between two elements. That is, there is some other product, say the product of matrices, let's say A times B, which of course is not the same as the Lie bracket, has none of these properties that we talked about. But from this product, you can always define a commutator AB minus BA, and this new product of two matrices would actually give rise to a Lie bracket. That is, to give rise to a product operation which has exactly the same properties that a Lie bracket must have. In fact, you don't have to keep yourself confined to just matrices. You can take a look at any associative algebra A which has a product, say let's call this diamond again, and one can obtain from such an associative algebra A corresponding Lie algebra G by demanding that G has the same underlying set as A does, that is the same underlying vector space, same field of scalars. But in addition, the Lie bracket operation is defined to be the Lie bracket of x comma y is x diamond y minus y diamond x. Of course, in the case of our matrix algebras, GLNF or SLNF, this is nothing but the matrix commutator. But in general, for any associative algebra A, which has its own product, you can define a new product by saying, take the product of x and y in the associative algebra, take the product of y and x in the associative algebra, subtract the two together, and now you have your new product operation, which actually has all the properties of the Lie bracket. To check that this has all the properties of the Lie bracket is essentially trivial. I will leave that as an exercise. So, given an associative algebra, you can always construct a Lie algebra out of it. We can talk about a Lie algebra in the abstract, on the other hand, without referring to any associative algebra from which it came, so that you don't have to think of the Lie bracket as xy minus yx. We can just think of it as an operation which takes in two vectors, produces a vector in a bilinear fashion, and has these two properties, and everything will follow from that. There happens to be a rather difficult result to prove in abstract Lie algebra theory, that given a Lie algebra, I can always find an associative algebra such that the bracket of the Lie algebra will follow from the commutator operation in that associative algebra. So in a sense that we can claim that if you understand xy minus yx, you understand all about Lie algebras. Now, while that is true, very often we will not need that. But at the same time, let me stress that in most of our applications, the Lie bracket will come from a commutator-like construction. That is, it will come from an associative algebra with a product, and there you would form xy minus yx, and you get the Lie bracket. Of course, if your associative algebra had a commutative product, then the Lie bracket would vanish identically. It would still be a genuine Lie bracket, would obey all the basic properties, but would be a rather useless thing to talk about. And so we are really interested in those cases where the Lie algebra gives you non-trivial results. At this point, I have a confession to make in advance. You can think of it as a sort of anticipatory bail application. While I did say that the Lie bracket may or may not come from a commutator bracket, old habits die hard, and for a physicist, as I have also said, very often the Lie bracket actually comes in because it's a commutator of operators. So I will often lapse into the physicist's habit of saying commutator when I mean the Lie bracket, or say that two things commute when actually all I really mean is that their Lie bracket vanishes. Since in most situations that we will apply this in, the Lie bracket really is a commutator bracket, this lapse of language, if you are being very pedantic mathematically, should not really lead to a huge amount of problem. Anyway, you have been warned, and at least in the rest of this lecture, wherever I say commutator or a commutator bracket, you should replace it at least in your mind by the word Lie bracket. Let us now turn to the question of how big a Lie algebra is. Now, except under very unusual circumstances, most non-trivial Lie algebras will have infinitely many elements. So the number of elements is not really a very good way to count or compare two Lie algebras. But since a Lie algebra is, after all, a vector space, we have a very easy way of talking about how big an algebra is, simply by looking at the dimensionality of the underlying vector space. So the dimension D of a Lie algebra G, written dim G, is a dimension of the underlying vector space. And that exactly is a measure which tells us how big or how small a given Lie algebra is. Now, closely connected with the notion of dimensionality of the vector space is the notion of a basis of that space. So if dim G is finite or countably finite, then we can write down a basis B of the underlying vector space with a countable sequence of elements from the vector space T1, T2, T3 up to Td if D is finite, or an infinite sequence of such T's if D is infinite, but countable. Now, the elements Ta of the basis B are called generators of the Lie algebra, and they are going to play a very important role in our study of the structure of Lie algebras. So, the generators of a Lie algebra are nothing but a set of basis vectors for the underlying vector space. Now, please note that the terminology is a bit, ambiguous here, in the sense that when we talk about Lie algebras in physics, we are seeing Lie algebra elements as generators of symmetries. But they are all, in that context, all Lie algebra elements are actually generators of symmetries, not just the basis elements. So when we say generators of symmetries, we could mean any arbitrary Lie algebra element. But in the context of the structure of the Lie algebra, when we talk about generators of the Lie algebra, all we mean are specific set of basis vectors of the underlying vector space. So, this is a confusion which might arise from similar language being used in different contexts, and so you have to be wary of that. Now, as we have just said, the most important thing about a Lie algebra is that it has a Lie product or a Lie bracket. We can actually describe the Lie bracket rather easily in terms of the Lie brackets of its generators. Remember, the Lie bracket is bilinear, so if you know what the Lie bracket of basis vectors of your underlying vector space, that is, of the generators, happen to be, then from that you can deduce the Lie bracket for any two arbitrary elements of the Lie algebra. So what is very important is the question, exactly what is the Lie bracket of the generators of a Lie algebra? So if we take two arbitrary elements from the basis, that is two generators of a Lie algebra, say Ta and Tb, since Ta and Tb both are Lie algebra elements, their commutator has to be a Lie algebra element. So it must be possible for us to expand this commutator in a linear combination of the basis vectors, which of course are again the generators. So the commutator of Ta and Tb must be of the form sum over C, C going from 1 to D, of the quantity f, a, b, c, tc, where the numbers f, a, b, c actually tell us exactly what the structure of the Lie algebra is, and that is why these numbers are called structure constants. Now, at first glance, there seems to be d cubed number of structure constants simply because the indices a, b, and c, which characterize a given structure constant, can each take d values, but because of the various relationships between the structure constants which follow from the properties of the Lie bracket, the actual number of independent structure constants is a bit lower than that. So let us now take a look at the constraints which these structure constants have to obey. Now, since the basic property of the Lie bracket is that the Lie bracket of an element of the Lie algebra with itself is 0, you must have Ta, Lie bracket with Ta must be 0, and this has to be same as sum over C, C going from 1 to D, of f, a, c, tc. So the linear combination of these basis vectors with coefficients f, a, c must give you 0, and since the basis vectors are linearly independent, the only way this can happen is f, a, c must be 0 for all a and c. That is, whenever the two upper indices in the structure constant are repeated, the structure constant must vanish. On the other hand, the other version for this antisymmetry demand, if you must remember, is TA comma TB is minus TB comma TA. And this, of course, implies that sum over C running from 1 to D of FABC TC must be the negative of the sum over C, again running from 1 to D, of FBA C TC. And because, once again, the fact that our TCs are linearly independent, the only way they can combine to give you the same result is if the coefficients are the same. So you must have this result that FABC must be the negative of FBAC. So these two are effectively the same conditions. They both follow from the antisymmetry property of the Lie bracket. We will now take a look at what condition on the structure constants is imposed by the demand that the Lie bracket, in addition to being anti-commuting, also obeys a special kind of non-associativity. That is, it obeys a Jacobi identity. And that is what we are going to turn to next. To see exactly what the Jacobi identity implies, let us consider three generators, TC, TA and TB, and form the double commutator that is used in the Jacobi identity, TC, TA, TB. Of course, this is just going to be one term in the Jacobi identity. You will have to take cyclic permutations of A, B and C to get the other terms. But let us just stick to this one term first. Now this one can be written as TC commutator with a sum over some index P running from 1 to D of FABP TP. This is just the definition of the structure constant being used here. But because the Lie bracket happens to be a linear operation, what we can always do is write this as sum over P running from 1 to D FAB P TC comma TP. And what we can always do is use the definition of the structure constant once again. So this becomes, this here becomes a sum over Q running from 1 to D once again of FCPQ TQ, or by interchanging the order of the sums over P and Q, I can write this as Q equals 1 to D summed over TQ with the coefficient, and the coefficient is sum over P running from 1 to D of FABP FCP Q. Now it is easy to see that the other two terms in the Jacobi identity, the ones which you get by cyclically permuting TC, TA and TB, will essentially have exactly the same form with the coefficients A, B and C here, these indices, being cyclically permuted. So ultimately what you will end up with is this term. Sum over Q running from 1 to D of TQ times sum over P running from 1 to D of a sum of three such quantities. One of them will be FABP FCPQ. Another will be FBCP FAPQ. This is of course what you get when you cyclically permute ABC to get to BCA. And finally, the next cyclic permutation will give you CAB. So FCAP, FBPQ. This whole sum over P has to multiply TQ, and this resulting thing has to be 0 according to the Jacobi identity. Once again, using the fact that the TQs are linearly independent, what this really means is that this particular coefficient that you have, each of the coefficients for every Q must be 0. So this sum over all P of FABP, FCPQ plus two other terms has to be 0, and this must work for all A, B, C, so it doesn't matter which generators you use, and Q, doesn't matter which of the generators you expand the result into. For all of them, you must have this particular sum equal to 0. So this is the condition which the structure constants must obey in order that the Lie bracket actually obeys the Jacobi identity. And this is going to play a very important role later on when we discuss the structure of the Lie bracket further. Let us now turn to the question of maps between Lie algebras. As we have said before, when we talked about groups, one of the most important things that you must study when you are studying an abstract algebraic structure is the kind of maps that you can have between copies or examples of such structures. And we are not really interested in any map between these structures, but in maps which preserve the basic algebraic structure that is there in the system. So when we are talking of Lie algebras, a homomorphism from the Lie algebra G to the Lie algebra H is a linear map. After all, Lie algebras are vector spaces. So the only kind of maps that we really want to talk about are those which preserve the linear structure of the vector spaces. And this is a linear map phi from G to H, which actually preserves the other important structure which a Lie algebra has, that is the Lie bracket. That is, such a map must carry a Lie bracket to a Lie bracket. That is, the Lie bracket of two elements x and y, and this works for any x and y belonging to G, must map into an element phi of x and y. This is of course an element of the Lie algebra H, but this must be the Lie bracket of phi x and phi y. Please note that the Lie bracket operations in the two Lie algebras may very well be different. However, what we want is, if you take the Lie bracket of x and y according to the rules of forming the bracket in the Lie algebra G, and then apply the map phi, the resulting thing would be the same as the one we would get by applying the map phi first to get elements of H, and then making or constructing a Lie bracket of those results using the Lie bracket defined in H. Now, if that happens for all x and y, which you can take from G, then this particular map phi is called a homomorphism. You should be able to appreciate the similarity of this particular definition of a homomorphism of Lie algebras with the one that we had defined for groups before. There, the all-important property was the group product. So a homomorphism was a map phi from a group capital G to another group G dash, which mapped the product of two elements of capital G into the product of the results of the map in G prime. Now, you may also remember that when we defined homomorphisms for groups, we had made the extra demand that the homomorphism be an onto map or a surjection. Now, as I mentioned then, this is not a universal part of the definition, and sometimes it's very useful to have that as part of the definition of a homomorphism. Sometimes having that is too restrictive. For Lie algebras, we will stick to this and only this as a demand for homomorphism. A homomorphism maps Lie brackets into Lie brackets. Has to be a linear map, of course. But at this point, we are not making any statement about whether a homomorphism is an onto map or not. In fact, depending on whether a map is onto or one-to-one, we have different names for homomorphisms. And let me just quickly tell you what those names are. This is a quick list of the types of homomorphisms you will see between Lie algebras. You don't really have to memorize all the names. Among all of these, the really important one is the isomorphism. But let me just go through the whole list anyway. If the map which maps G to H is an injective map, that is, it's a one-to-one map, then the official name for such a homomorphism is a monomorphism. And very often the symbol we use when there's a monomorphism between H and G is this kind of crooked arrow or bent harpoon, that H is sort of included in G by this. We will talk more about inclusions later. The homomorphisms which are actually surjective or onto are actually called epimorphisms, and the nomenclature for that, or the notation for that, is H has a double-headed arrow pointing towards G. As I said, the most important example is, or most important kind of homomorphism is an isomorphism, and that is when a homomorphism is bijective. That is, it's both injective and surjective, and frankly, if you have an isomorphism between two Lie algebras, they are essentially the same Lie algebra. Once again, let me remind you of this is exactly the same as what we had for groups. As far as group structures is concerned, two groups which are isomorphic to each other are essentially the same group. The same can be said about Lie algebras. Two Lie algebras which have an isomorphism are essentially the same as far as Lie algebraic structure is concerned. And the notation for that is H with this tilde equal to sign between H and G. Now, two other kinds, specific classifications of homomorphisms are very important. All these homomorphisms that we have been talking about are in general between two different Lie algebras, but if you have a homomorphism from a Lie algebra G to a Lie algebra G itself, it's called an endomorphism. Endo, of course, meaning inside. And another special nomenclature is that if this map from G to G happens to be an isomorphism, then it is actually called an automorphism. Once again, the nomenclature is very similar to what we have for groups. You have to just be careful when you're using it to remember whether you're using these nomenclatures for groups as opposed to for Lie algebras. While homomorphisms form a very important class of maps in the subject of the theory of the structure of Lie algebras, there happens to be another important class of maps from G to G, which are very important despite the fact that they are not homomorphisms, that is, they are not endomorphisms. These maps are called derivations. A map delta from G to G is called a derivation if it obeys the following property. For every pair of elements x and y taken from the Lie algebra G, the map delta acting on the Lie bracket of x and y gives you the Lie bracket of x with delta acting on y added to the Lie bracket of delta x and y. Now, the reason why this is called a derivation should be very obvious. If you remember, the way in which the derivative acts on the product of functions is exactly this. You differentiate one function, leave the other intact, so that you add the result of the first function times the derivative of the second. This is exactly what is going on here. And when you remember that the Lie bracket is actually the product when Lie algebra is concerned, the name derivation becomes very obvious. In fact, derivations happen to play a very important role in the structure of Lie algebras, and the reason behind that is because they behave very similarly to the way derivatives behave on ordinary functions. Now, more on that later, but let me just give you an example of a derivation. And this is an example which you have all met before, This is the adjoint map. Let me just remind you that for any x belonging to the Lie algebra G, you can define a map, add x, which maps G to G, and you define this map by saying that its result on any element of G, so for all y in small g, of course, add x acting on y is nothing but the commutator of x with y. Now, the claim is that this particular map is a derivation. And to check whether it is, what we need to do is apply add x on a Lie bracket. Let us take the Lie bracket of two elements y and z of the Lie algebra. So add x acting on y and z is of course the commutator, or the Lie bracket rather, of x with the Lie bracket y comma z. And then what we can always do is rewrite this using the Jacobi identity. The Jacobi identity of course has three terms which are added up and you get 0. So this is one term here. This must be equal to the negative of the other two terms. So minus y comma z comma x minus z comma x comma y. Now we can write the brackets inside both of them in terms of add x acting on some Lie algebra element. But before we do that, let's change the minus signs to plus. This one can be changed to a plus while keeping y in the first position, simply by switching the relative positions of x and z. Remember, the Lie bracket is anti-commuting, and applying the same kind of anti-commutation here by flipping the relative position of z and the Lie bracket x and y, we can rewrite this with a plus sign as well. And now notice that the Lie bracket x comma z here is nothing but add x acting on z, and the Lie bracket x comma y in the second term is nothing but add x acting on y. As a result, this is just y and add x z's Lie bracket added to add x y and z's Lie bracket. This is exactly the property that you need for a derivation. The fact that the add x operator is a derivation will be of immense importance in our later discussions about the structure of Lie algebras. Now that we have taken a look at maps between different Lie algebras, we have to turn to the other aspect that we have to pay attention to whenever we are looking at a new kind of abstract algebraic structure, and that is the notion of substructure. In this case, because we are talking of Lie algebras, what we are trying to look at now are Lie subalgebras. Now, a subspace H of a Lie algebra G, remember, a Lie algebra is a vector space, so a subset can also be a vector subspace, and we are talking of such a situation. Now, a subspace H of a Lie algebra G is called a Lie subalgebra of G if it is itself a Lie algebra, and just as in the case for groups, this has to be a Lie algebra under the same Lie bracket operation that was there in the original algebra, which is often also called the ambient algebra. So in this case, H is a subalgebra of G and G is an ambient algebra of H. We don't usually use the word superalgebra as opposed to subalgebra because that has a different meaning. In order to discuss subalgebras and related issues, it is actually quite useful to introduce a new notation. And this notation is that of the commutator of two subsets, H and K of a Lie algebra G. Note that here we are making no assumption whatsoever about whether H and K are subalgebras in their own right. They are just subsets of the underlying set of the Lie algebra G. The commutator bracket or the Lie bracket of H and K is defined to be the span over the field F of all the commutators of elements which you take from H and K respectively. In case you have forgotten this, let me just remind you, the span is just a name of a collection of all possible linear combinations. So here, in order to form the Lie bracket, so to speak, of two subsets H and K, what you really need to do is take elements from H, elements from K, take the Lie bracket and take all possible linear combinations of those Lie brackets. And that is what we are going to call the Lie bracket of H and K. So what we have done is we have generalized the notion of the Lie bracket from elements to subsets. Now, in the language which is facilitated by this notation, we can immediately say that a subspace H, which is a subset of G, is a subalgebra if it obeys the following. The Lie bracket of H with itself has to be contained entirely within H. Because note, that is the only real condition that we want to impose here. If you take any two elements from H, their Lie bracket has to be in H itself. At this point, let me state something which is pretty obvious. Every Lie algebra G has two subalgebras for sure. One of them is G itself. The other is the trivial subspace with only the vector 0, the null vector in it. And it is easy to check that this has to be a subalgebra according to the definition of a subalgebra that we have just laid down. So, these two subalgebras, which every algebra has, irrespective of their structure, are called trivial subalgebras. And frankly, these are the ones we usually pay very little attention to. When we usually say subalgebras, what we really mean are proper subalgebras. Proper subspaces of G, which are not the null subspace, and which actually are Lie algebras in their own right. However, the existence of trivial subalgebras has to be borne in mind because very often the fact that an algebra does not have anything other than a trivial subalgebra may have very important bearing on its structure. Let us now focus our attention on a very special kind of subalgebra which some Lie algebras may have. This is the notion of what is called an ideal. An ideal of G is a subalgebra which obeys a much stronger condition than the condition which defined a subalgebra. For something to be a subalgebra, it has to be closed under the Lie bracket operation. That is, if you take any two elements from that subalgebra, their Lie bracket has to be in the subalgebra itself. To qualify as an ideal, what must happen is that if you take any element from this ideal and any element whatsoever from the original Lie algebra, the ambient Lie algebra, the resulting Lie bracket would have to be in the subalgebra itself. So, the Lie bracket of the set H and the set G is actually contained within H. This is of course much stronger than the condition for a subalgebra, which was simply the Lie bracket of H with H has to be contained in H. Here, the Lie bracket of H with all of G has to be contained in H. Now, I did say that we are not going to talk much about Lie groups in this lecture because the connection between Lie algebras and Lie groups, we have already seen some of it. We will see a lot more of that later, but for the time being, we are focusing on Lie algebras themselves. But at this point, I cannot resist saying at least this much. The notion of the ideal of a Lie algebra is intimately connected to the notion of an invariant subgroup or a normal subgroup in the case of a Lie group. And just as you have seen that normal subgroups are very, very important in deciding the basic structure of groups, in the sense that a group may be thought of as direct product of its normal subgroups, hence being built up of smaller groups and so on, you will see that ideals which a Lie algebra may have play a very important role in deciding the structure of the Lie algebra. Now, just as before, it is obvious that the Lie algebra G itself and the trivial subalgebra with only the null vector in it are not only subalgebras of G, they are also ideals of G, but they are rather trivial ideals of G. A proper ideal of G is an ideal which is neither of these two. And of course, not every algebra may have a proper ideal. Now, just to give you an example of an ideal, let us talk of a very special subalgebra which a Lie algebra has. This is called the center of the Lie algebra G, denoted by Z of G, and this is defined to be all the elements of G which have vanishing Lie brackets with each and every element of G. So Zg is nothing but those elements which, so to speak, commutes with every element of G. Now it is rather obvious that the center is an ideal of G, simply because if you take the Lie bracket of the center, this subspace, and the entire Lie algebra G, what you are going to get is a singleton element with only the null vector, which is definitely contained inside Z of G. So this is an example of an ideal. Now, it's possible that some algebras may have a proper center, that is a center which is not the null vector alone. On the other extreme, for an abelian Lie algebra, every Lie bracket vanishes, and the center of an abelian Lie algebra is the entire Lie algebra itself. We will have a lot more to say about subalgebras, ideals, and how ideals built up bigger algebras and so on in later lectures. But for the time being, let me just show you how these statements that we have made about subalgebras and ideals translate in the language of structure constants. As I have said before, the structure constants have complete information about the structure of a Lie algebra. So it should be obvious that these rather important notions can be stated in terms of structure constants only. Now, in order to see this, let me remind you that a subalgebra, any subalgebra H of G, is a subspace. And being a vector subspace, it has its own basis. So let Ta1, Ta2 up to Ta prime be a basis of H. We have assumed that D prime is a dimensionality of this subspace H. Now, it's a very standard result in linear algebra that you can always expand or enlarge a basis of a subspace into the basis of the whole space. So you can always extend this basis to form a basis of G, of the Lie algebra G. And here what we have done is we have written down the first D prime basis vectors, which are basis vectors also of H in blue, and the other basis vectors have been written in orange. These are TB1, TB2, TBD double prime, where D double prime is defined simply by this relation that D double prime plus D prime is a dimensionality of the Lie algebra G. So now what we have done is we have chosen a rather special basis in which the letter A with indices 1, 2, 3 up to D prime actually stands for the basis vectors or generators of the subalgebra H, and the other generators, those written with B1, B2 up to BD double prime, are generators which are not elements of the Lie subalgebra H. Now the fact that Ta1, Ta2 up to Ta double prime spans the subalgebra H simply tells you that the moment you take a Lie bracket of any Tai with Taj, where I and J can be taken from 1, 2 up to D prime, this must be an element of H, the subalgebra, and hence it cannot have any component in the direction of TB1, TB2 and so on. So what we must have is FAI, AJ, BK must vanish. That is, if the upper two indices are taken from generators which refer to the subalgebra, and the lower index is taken from a generator which does not refer to the subalgebra, the structure constant must vanish. So this actually is the structure constant version of the statement that H is a subalgebra. Let us just quickly look at what structure constants have to say about ideals. And that also is pretty simple. If H is an ideal of G, then if you take the Lie bracket of Tai, where Tai is any one of the generators of H, with Tx, where Tx is any one of the generators generator of H, not a generator of H, does not matter, any one of the generators of G, then the Lie bracket of TAI and TX must be an element of H, and hence this immediately tells us that it will have zero coefficient for any one of the TB1, TB2 up to TB double primes. So what we are going to have is FAI x Bj has to be 0. And this is what characterizes an ideal in terms of structure constants. If one of the upper indices in the structure constant happens to be from the subalgebra, in this case from the ideal, and the lower index happens to be from outside the ideal, then irrespective of what the other upper index is, the structure constant must vanish. So as you can see, of course, that this is a stricter demand than in the case of merely a subalgebra, which is why all ideals are definitely subalgebras, but all subalgebras are not necessarily ideals. Now, in this lecture, what we have done is we have laid down the groundwork for the abstract theory of Lie algebras, while our interest is in concrete physical applications. Being conversant with these abstract notions will actually stand us in good stead later on when we want to apply them directly to physical problems. We are actually going to continue with the abstract ideas a bit further. We are going to take a look at representation theory of the algebras, but even before that, what we are going to take a look at is how a given Lie algebra may be built up out of the ideals and other subalgebras, as we have hinted in this lecture. But all that is for a later lecture. Bye for now.